So we have here y equals the natural log of x, or ln of x. So this ln stands for the natural log, or log natural. Now, we haven't looked at logarithms. Just by show of hands, has anybody in here actually seen logarithms before? Okay, so a couple of you. Have you met this thing, the natural log? Yeah? Okay. Good. Now, we will look at this. We will look at this in a little while. But just for the moment, logarithms are the reverse of powers. Okay, they're the opposite of dealing with powers. So if I give you something like this, let me deal with that. Just go like that. Okay. What would this x be? So I've got 3 to the power of x equals 9. What would x be?
3.
Good.
Logarithm. Oh.
It would be 2, right? Yeah, exactly. So it'd be equal to 2 because you're saying 3 squared equals 9, right? But what if we didn't know what x is? Because, for example, if I change this to be, for example, 8, and then I ask the question, what's x equal to? This is harder, right? This is harder because you don't know, well, 3 to the power of 1 is equal to 3, 3 to the power of 2 is equal to 9, so it's got to be somewhere between 1 and 2, but you don't know exactly what it is. So what logarithms do is they basically rewrite this thing so that you can deal with the power if you don't know it. Okay? So yeah, that's fun. What were you going to say? So it'd be log. In this case, what would the logarithm be?
2.
So would it be 3
Yeah.
of 8? Like that.
Then I make like 3 times.
Yeah, exactly.
2 times 3 then.
Yeah, good. So basically, this is just another way of rewriting this. That's all a logarithm is. That's all I want you to understand as a logarithm for the time being. And we'll do more practice on this. But then the question is, well, how could I look at the logarithm graph? Well, it's a similar kind of idea to what's happening down here with the functions. Okay. This, if you understand what this graph looks like, because this is a kind of inverse, it would just be a reflection of the line y equals x. What would this graph look like? Y equals 3 to the power of x. What would this graph look like? Any ideas? So okay, let's do a table of values then. So what about if we do x against y, and we go for, okay, let's go -3, -2, -1, 0, 1, 2, and 3. Okay. So those are my x values. What are my corresponding y values? Right? So let's stick with an easy one. Let's go 1. X equals 1. What would y be if y equals 3 to the power of x? It would just be 3, right? Because it's 3 to the power of 1. If x equals 2, what would y be? 1. And if x equals 3? Good, okay. Anybody remember what would 3 to the power of 0 be? 1. What would 3 to the power of negative 1 be? 1 over 3, good. Remember that if you raise it to a negative power, you just do 1 over and then raise it to the positive power. So what would 3 to the power of negative 2 be? And what would 3 to the power of negative 3? Okay. Are you happy this thing is never going to go negative? Never going to go negative. Is it ever going to reach 0? It's going to get pretty close, but it will never actually reach 0. And are you happy that this thing is growing pretty quickly? Like every time we go across by 1, we're basically going up by 3 times the amount. So 1, 3, 9, 27, 81, 243, for example. So it's growing really, really quickly. So we just need to draw a graph that grows really, really quickly and never reaches 0. What about that? Would that fit the bill? Because you're happy it's getting closer to 0, like as we carry on in this direction, we're going to get smaller and smaller and smaller, but we're never actually going to reach 0. That fits that bill. Okay. And are you happy that as we move across in this direction, we're getting bigger and bigger and bigger and bigger? This is also getting really big. Okay, it's getting much, much steeper as we move across. Okay. So this would be the graph, y equals 3 to the power of x. Now, I haven't given you that graph, I don't think. Just quick check. Or have I missed something? I've missed something. Sorry, I missed a page out. So actually, if you look at number 6, it's got y equals e to the power of x. Okay? Now, e is just a number. We'll look at e in good time, but just think of it as like 3 to the power of x. So actually, if you look at number 6, this is the graph which you should have drawn. Okay? Or a graph like this. By changing this value, will just affect the steepness, how quickly it grows. Okay? But it's still this kind of shape. Okay. Sorry, I missed those 2 out. So that should be number 6, y equals e to the power of x, or y equals 3 to the power of x. Doesn't matter. Does anybody know what type of graph this is? So this one was obviously a linear graph, this was a quadratic graph, this was a parabola, this was a cubic graph. What would this one be? Does anybody know? Anybody know the name of this type of graph? We would call it an exponential graph. Okay? Because it's to do with the exponent, the power. Yeah? Remember, exponent is another word for power. So an exponential graph. Effectively, this is a graph that grows really, really rapidly. This type of relationship, you see it in nature quite a lot. For example, if you imagine, you have people in a room and they start reproducing with each other, then all of those offspring will then start reproducing with each other, then all of those offspring will start reproducing with each other. Suddenly, this population is growing really quickly. Does that make sense? Yeah. So exponential just corresponds to a really rapid type of growth. More specifically, it's a type of growth where you're multiplying by 3 each time. Okay. So you move across by 1, and you multiply by 3. Okay. Now this logarithm graph, so number 7 now, let's come to that one. The logarithm graph, so this one here, y equals log to the base 3 of x, or y equals log to the base e of x, or y equals natural log of x. A logarithm graph should just be the inverse of this. Now we've just seen with this, over here, that the inverse is just simply a reflection, the line y equals x. So if I draw the line y equals x on here, I would get something that looks like this. Okay? Y equals log x, something like this. Now, if I'm going to reflect that, in fact I've drawn that a little bit steep, let me just go back and correct that. It's probably a bit fairer. Okay. The logarithm graph will just be a reflection in this line here. So if I reflect this graph, or the exponential graph, in the line y equals x to get the inverse, I should get something that looks like this. So that there would be the natural log graph. So we draw that in. Okay, something that looks like that. Now you see how I've drawn this. It kind of flattens off, okay, but it never truly becomes flat. So it's still always growing. It just slows down. Okay, so here it's growing really, really quickly, but over here it's just slowing down slightly. Now this will make more sense when we do logarithms, and the advantage of course of filming the lessons, then you can go back and re-watch them once you've looked at logarithms, so that might make a bit more sense once we've done that. But effectively, if you take nothing else away, you take away what these graphs look like. You need to know what every single one of these graphs look like in here, okay, which is why I've given them all to you now. So it's almost like a library of functions that you're building up. Because in an exam situation, for example, I can turn around to you and say, Ahmed, could you draw the line y equals log of x? And I'd expect you to draw that graph. And then can you draw the line y equals 3 to the power of x? And I'd expect you to draw that black graph. Okay? So this is what I'm kind of building you up to. So if you just remember the graphs, that's fine, but what I'm trying to give you as well is some key skills, so that if you can't remember what the graphs looks like, you can always go back and think about it and try and work it out.